Today's video, I will try to give you a brief idea about definite integral by definition, or as they say, definite integral as the limit of a sum. Okay, so let's go quickly to the meaning of the definite integral. This is a very familiar symbol, integral a to b f of x dx. This is the definite integral of the function f on the closed interval ab. So basically we should have written ideally these limits run on this variable. Now what does this mean? It means this is the area enclosed by the curve y equals to f of x, the x-axis and the ordinates x equal to a, this vertical line, and the other ordinate x equal to b. So basically, just to illustrate, we have taken a function. To be specific, for this type of definition, the function needs to be continuous. That is to say, you can be able to draw the function, the curve, without lifting your pen. This is just an example. So it runs from the closed interval a to b. Now, this whole region, the area of this figure, is denoted by this one. So this is nothing but the definite integral. Now, how to get an expression for that? We are going into that. Okay. So let the total area be S. Okay. So S is basically this whole shaded region. Now, you notice that the three sides are parts of straight lines. The only problem is this. We don't know what this is. So obviously it depends on the function. Okay. So what do? We quickly divide this whole interval into parts, equally spaced parts. So if I want to divide it into, say, n parts, I'll name the first point as x0, the second point as x1, x2, so on and so forth. The last one would be b, which is xn. So the previous one, the penultimate one, would be xn minus 1. Okay. So just to give a general idea, any strip in between will be xr to xr plus 1. It's getting a bit clumsy here, but we'll manage. So what does it do to this area? It divides the whole area into strips. Strips like this. So first strip, if I were to draw, it would be looking like this one. This is the second strip, somewhere here. The rth strip will be this one. Okay. So we focus on this rth strip. We focus on this. Let's, for instance, zoom it. Have a look at it. I've written in this form. So this is the rth strip. So what are the endpoints? X equal to xr and x equal to xr plus 1, right? Now, does this look like a rectangle? No, it does not. It would had this been a line parallel to this one, but it's not. The problem is because this here, this carved part, is a part of this whole curve. Now here comes the calculus into play, right? Now we have divided this subinterval, this interval into parts. And if there are n plus 1 points, x0, x1 and so on, so there would be n parts. So the whole interval AB is actually in reality x0 to x1 union x1 to x2 union so on and so forth, going up to xn minus 1 to xn. So what do we have here? We have here n equally spaced subintervals, the total of which, that is if you take the union of all of them, you get the whole AB, right? Now note that they are equally spaced, okay? And if the width of each of this subinterval be h, and there are n subintervals, then what do we have? Obviously nh would be the total width. Once again, coming back to the curve, what is the length of this part? It's b minus a. So nh, that is if you add all the widths of these subintervals, should be equal to the length of the original interval, which is b minus a. So keep this in mind. This is a very important part of the whole process. nh equals to b minus a, right? Now, as I said, here comes the calculus into play, the limits. So what do? We make n large. Sounds familiar? Yes, n tends to infinity. Make n large. So looking at this. This is like a piece of paper. You put it into a shredder. So each strips you get, the number of strips, if you have increased it, then the thickness or the width of each strip will be reduced. So to say, if you increase n, if you make n bigger, h becomes smaller. So as you make n big, h, that is the width, tends to 0. This is another important idea which we will be definitely using. Now, let's come back here, right? This is h, no doubt about it, right? Now, as the strips have become thinner and thinner, this will not matter anymore. Try to understand the notion. For instance, we take the left wall in this one. Now, what would be the y coordinate of this point? Obviously, this point, the x coordinate is xr, and this is a part of the curve y equals to f of x. So, this will be, the y coordinate will be f of xr. So, this point will be xr comma f of xr. So, looking at it, this left wall has the height f of xr. Now, if we were to consider this rectangle, this rectangular strip, what would be its area? H times f of xr, length into breadth. So, area of this rth strip, this is the rth strip, will be h times f of xr. Note that we have taken the area of the rectangle, but I have written the area of the rth strip, which is this one. Why? Because of this limiting condition. As the width of the strip becomes very, very thin, this roof does not matter anymore, because these two walls are very closer to one another. I have just magnified it for your convenience. Try to visualize it. So I hope you understood what I mean, because this will be approximated to the area of the rectangular strip, right? So now here's a quick thing. Since x1, look at the point, is h distance away from x0 or a, so x1 could be written as a plus h. Similarly, x2 is again h distance apart from x1, so it's 2h distance apart from a. Following this pattern, xr will be r times h distance away from a. So we are going to use this one. We want to put it here. So what do we have? H times f of a plus rh, right? So coming back to the whole picture, this whole S. S is the usual notation for area. Area under f of x. Can you write it like this? I think some people did, but somehow it got morphed into this. So S of f of x, or for us it's a to b f of x dx. And what is it? It will be the sum of all these strips, right? So sum of all these strips. So h f of x0 plus h f of x1 plus going up to h f of xn minus 1, right? But of course under the limiting condition that n tends to infinity, right? Now can we do anything with this term? Of course we can. H can be taken common, and the inside f of x0 plus f of x1, this can be written as f of summation of f of xr, where r ranges from 0 to n minus 1, right? Now as we have found, it's nothing but xr can be written as a plus rh. So here we have it. This is the form. Either you write this, or you may also write this. Optional. Because as n tends to infinity, h tends to 0. So finally what do we have? Integral a to b f of x dx is limit h tends to 0, h times summation r equals to 0 to n minus 1 f of a plus rh. This is your expression, required expression. Now you must be wondering, we have taken the left wall here. What would happen if we approximated with the right wall? Well, nothing much. If you had considered this one, right? So what would be this height of the right wall? It would be f of x r plus 1, right? And doing this in the same way, the only difference would be this term. So we have this, and the summation will be like this. Note that instead of writing r plus 1 running from r0 to rn minus 1, we have changed the limit. We have replaced it by r. So now the limit runs from 1 to n. So this is also another expression of integral a to b f of x dx. Similar looking, only difference, the limits of the sum. But does it actually make a difference? If you look at the big picture, how many strips are there? N. And n is tending to infinity. So actually it does not make any difference at all. You can write either this 0 to n minus 1 or this, right? Note that you have to write this one. This is crucial, that nh is equal to b minus a, depending on the limit, and the definite integral depending on the function. So this much for today. Of course, this idea can be extended to advanced concepts, but for the time being, I think this will be helpful. Okay, so thank you.